like this. I think if they do that diversion, yeah, they might become the next one. But it was one of those, they want to do it for guys.
That'll all go away. I know you're good.
Thank you.
Yeah. So I guess.
And then let's just make sure you're. Can you just click over?
Yeah, I think that works.
Alright. Hello everyone, we're gonna get started now. Thank you for being here today. I'm pleased to introduce Dr. Chang. Dr. Chang is currently a postdoc fellow with a Wang Materials Group in the Maketa Department of Chemical Engineering at Austin, where he's been there for the past year and a half, I would say. Yeah. He received his PhD in physical chemistry at Temple University in 2023, where he built on the Frenkel-Holstein model to include inter and intra molecular charge transfer. And he is currently applying this expanded Frenkel exciton theory in absorption and emission spectra for copolymer chromophores. Jin is an early career scientist that does outstanding work, and we are excited to have him out here due to the Meet Up Friend partnership with UT Austin. So please help me in welcoming him.
Good morning, everyone. Thank you for coming, and thank you for the kind invitation from Dr. Gabriel. It's really my great honor to share my research here. I should make this story for back when this summer we met at the UT campus. By accident, my current PI doesn't show up. I just present my research in our ER building. That's an engineer for the education and research building. That's pretty advanced in technology. And in the beginning, he just said are you gonna give us a talk in our university? And I was totally astonished. Is that some did I make some mistake in listening? Because I'm only a postdoc, and how could he just how could he invite me? I'm totally astonished. And then he confirmed that so we're gonna invite you to our NAU. Wow! So I said that's my great pleasure to share my research here. So that's the reason why I'm showing up here today. So for quick table contents, just we'll go through the conventional Kasha theory, and then just we will have some non-Kasha behavior, just the new features in just found in the chromophores, and then just if we still have enough time, we will go over my current research result, singlet-fission in the PDIs. So. And here, show some our research results. If you like, you can just scan the QR code and find the reference. So as we know, experiments the chromophores for much of the optical electronics, such as the solar cells, sensors, or the semiconductor, and maybe even in the future spin qubits in the quantum computing, and the spectra is the gateway to the underlying physics of that. So in the pump probe experiment, so we can definitely see the vibronic progression in the spectra. So that's the known as the Kasha features or Kasha phenomena in the vibronic signature, right, of the spectra. So engineering the structure of the molecules just tunes the packing behavior of the in the aggregates, right? So and not only on the the packing distance, but also the sleep with respect to the neighbor chromophores, right? So then we can definitely see that the different features or in the aggregates. So here is a practical example, so the dash black curve is the absorption spectra in the THF solution. We consider it as a monomer case, and then just in the aggregates, the two robust features appear. First, the whole band, and you can see the whole band just had a redshift, and I should say that really depends on the intermolecular the phase of the intermolecular coupling. It's just and then just you could have either redshift or blue shift. And then the other feature in our in the current spectra is A1 gains the huge intensity over A2, right? And that's the A1-A2 ratio is much greater than the monomer case. That's the vibronic features in the absorption spectrum, right? And Frenkel first proposed a mechanism to understand the exciton behavior in the aggregates, and so we still use that theory in the organic solid nowadays, right? So let's start from the localized exciton picture, and that means if we excite an electron in this molecule, and then just one electron goes excited from the HOMO to the LUMO, leaving a hole at the HOMO. And then just if we consider the electron hole bonded on the chromophore as a exciton, and then just we can just denote this state as like on the chromophore 1 as state 1, so like this. And since we know in the aggregates the chromophores interact, right? So the exciton will not stand still on single chromophore. It can just transfer through the the Coulomb-coupling, right? And the forms a delocalized exciton states. So so the dominant resonant term is their Coulomb-coupling, and in the most method, we just use the dipole approximation. So the and then just after we diagonalize the whole Hamiltonian, we can have and also we include only the nearest neighbor coupling, and then just the total wave function is plane wave one. So and then just in the pump probe experiments, we can use this the H energy as the estimation or the ground state bleaching or the stimulates emissions, right? So later, Kasha tried to think about the relationship between the band shift, the band shift in the absorption spectra and the aggregates, and so as we know, the molecule should have then here's the simplest case, a dimer. So they both have the transition dipole moments. So and then when we know they could be coupled through the Coulomb-coupling. So in the beginning, if the two chromophores are the face to face, or so cofacially aligned, and then just the with the dipole approximation, the Coulomb-coupling is a positive number. And then, as we know, in the adiabatic states, sorry, there's no laser. So we know the energy of the exciton state will just split, and their splitting is estimated by the 2 times the strength of the Coulomb-coupling. And we know in the two level system, like one of them is in phase state and the other one is out of phase, right? And since the Coulomb coupling is positive, so the in phase state will go to the top of the band, and so in the in phase state has the same parity symmetry with the electronic ground state. So then the electronic transition is allowed, but the out of phase state, since if under the exchange symmetry, like it gains a negative number, so then that means the parity symmetry is odd, and then just the transition is forbidden. This transition is forbidden, so we call it the dark state. So here, for the total picture, we call it like H-aggregates. And then just if we allow the one of the chromophore slide a little bit, and we can have like a head to tail coupling. So the face of the Coulomb coupling just totally flips over, and that means a negative number. And then just the whole picture is similar, except the bright state goes to the bottom of the band. And so that's the different. That's like two different contrasting like picture of the H and J aggregation. So if we compare the adiabatic exciton state in the aggregates. So if the Coulomb coupling is positive, so the bright state goes to the top of the band, and then the total energy level of the bright state is much greater than the monomer case. So that means the absorption the absorption band should go to the upper energy level. So or we can call it blue shift as shown here. But if we have the J aggregates, so the bright state stay at the bottom of the band, and then just it only. So that means the whole bright band should have red shifts, right? So here's the info take home, right? The J aggregates the red shifts, and the H aggregation is just blue shifts. And since we believe the lowest excitonic state should emit, so we can conclude that in the J aggregates the is super radiant, but in the H aggregates, since it's the in this stage just stay above the at the top of the band, so it's non-emissive to, or in experiments we call the photoluminescence is crunch. So that's the typical feature of the Kasha theory. Since we have just the band shift, where the exciton sits with Kasha theory, and now we turn to think about how the vibronic progression looks like. So in the displaced harmonic oscillator model, we assume the potential energy surface of the electronic ground state and the excitation state both harmonic, or the perfect with the same curvature, and then we believe they are the perfect parabola, and then you can see there the electronic transition energy is H bar omega 00. That's the 00 transition, and the pure electronic one. And then just the interesting point is in the excitation state, the potential while just displays along the nuclear coordinates by lambda. So because in the excitation state, it has part of the open shell features, right? So the equilibrium bond lengths of the like chemicals in the excitation state is a little bit greater than the ground state. So if you check the isolate, so the C2H4, like in the excitation state, the carbon bond like is around like 0.02 or 0.03 angstrom longer than the ground state. So that's the reason why the Holstein just believe the potential energy surface of the excitation state is just displaced a little bit. So since like the in the nuclear coordinates like the just displayed by lambda, so we can estimate the energy just induced by this translation is around like lambda square, right? So since they are all like perfect parabola, and but we have to know that in the quantum oscillator, their energy level is scaled by the h bar omega. That's the vibrational content, how many vibrational content. So we pack the whole like the parameter as dimensionless one, this which known as Horn race vector, right? So under the Frank content limit, like we can definitely show the vibronic progression follows the boson distribution, and the spacing or like the energy difference between the A1 and A2 peak is just the h bar omega bar plus the energy difference between the vibrational content, and then the ratio of the first two peaks is A1 A2 ratio is equal to 1 over the Horn race factor, or 1 over the lambda square. So the lambda square, we use the lambda square at the Horn race factor, right? So that's the vibronic progression. So put them together here, like I show benchmark calculations. So on the left hand side, like I set up a J aggregates, and by the negative Coulomb-coupling. And you can see the black dash curve is the absorption spectra in the monomer, and then just you can see they both have the whole band shift to the lower energy region, and then that's the A1 peak gains huge intensity over A2, and but on the right hand side, by flipping over the Coulombic coupling, and it has a whole band just blue shifts, and then just the A1 peak is compressed huge amount over A2, right? So here, that's our scoreboard for the Kasha HJ aggregates. We add one more term, so the A1 A2 ratio. So in the J aggregates, just a great. It's enhanced. The A1 is enhanced, and the H aggregation is just totally compressed or annihilates, right? So that's the typical feature. We should just keep that in mind. So we know, in our experiment, we every day, we just make lots of really new situation or new phenomenon which contradicts the old theory or old experience, right? Here's an example. So Ponzi et al. Just synthesize two different DPP bisulfine derivative, which only differs at the termini group, cell acetal group versus the methyl group. And if you check the absorption on the right hand side, they both have it has a obvious redshift, and the aggregates that means the thin film organic nanoparticles, and then just but the report is totally non-emissive, and that's totally contradicts with the Kasha theory, like because the J aggregate should like super radiant, right? To understand that mechanism, so we have to just look into the like structure of the chemicals like the EPPs. So it's known as a donor, acceptor, donor, like chromophores. So like two like bisulfine donor units just flag the acceptor EPP in the end center. And the energy level diagram is really interesting. Like the HOMO of the donor sat just like almost aligned with the HOMO of the acceptor, but the LUMO just of the acceptor is around 1 lower than the LUMO of donor. So for simplicity, like in the future, I will use the DAE stand for the whole chromophore. So let's get back to the absorption spectra of these two species and like take a closer look at them. Just let's focus on the aggregate case. So on the left-hand side, like in the cell asto species, like the whole band has a huge redshift, right? As you can see, and the A1 A2 ratios is the A1 intensity like is totally like enhanced over A2. That's a little bit larger than the monomer case, right? And so that's the like classical Kasha J aggregate signature, right? And then just if we check the one on the right hand side, like it has a bunch of the redshifts, the whole band of redshifts, right? And then just that's the feature of the J aggregates, right? And then just if we check the A1 A2 ratio, that's like the A1 is totally like annihilates in the intensity over A2, right? So it's like typical the H aggregates. So if you still remember like the Kasha signature in previously showed, and we put them together as for comparison, the left hand side one, the cell acid derivatives like classical like a textbook like Kasha J aggregates, but like for the methyl derivative, like it has a J like the J lag band shift, and but if we check the ratio, it's like A1 is much smaller than A2, and also the if you check the photoluminescence, so like Ponzi reported, like it's like the PL is totally quenched. So the last two features are the typical H aggregation, right? So that means we both have the redshift and H aggregation in the same chromophore, or you can also call it like non-emissive J aggregation. So they are the same thing. So that means like these mismatch, like there must be some like actual short range physics behind like beyond the dipole interaction. So in the following, like I try to use the like a really simple like Frenkel Holstein CT model to like reproduce both the like the band shift and the ratio of the like peaks. So let's start from the like the monomer, like the only one DAB chromophore, and as I have shown, like the LUMOS has like 1 eV around 1 eV shift down, right? And so we can just anticipate that like excited electron, then in the donor side, the electron density tends to move to the acceptor unit to just stabilize the whole system. So it's like the p-n junction in the semiconductors, right? So we can anticipate that there should be the huge dominant features and charge transfer features in the absorption spectrum. So to consider so after considering the charge transfer state, then that means the exciton could couple there should be two coupling pathways. So the neutral exciton could just directly couple through the Coulomb-coupling, or they can just have incoherent transition between donor acceptor through the CT states. So to visualize them, I just have really simple animation. So if we excite, let's start from the localized donor exciton picture, right? And then we can allow the electron just transfer from the LUMO of the donor LUMO to the acceptor LUMO, and they're the Hawking integral could be estimated with this equation, and then we can also let a hole transfer from the donor HOMO to the acceptor HOMO. But in practical, as you can see, that's opposite electron transfer from the HOMO of acceptor HOMO to donor HOMO. So, but by convention, maybe we name it as a hole hopping. So, and then just we have a negative sign to stress that it's a reverse, it's an opposite way, to couple them. And then by symmetry, and for symmetry, we can still have a start from the acceptor localized exciton. So they're the same, they have same features. And then when we consider the aggregates, so there should be more the chromophores, and we only consider the nearest neighbor coupling, and then just we can let the electron transfer from donor HOMO of the first chromophore to the HOMO of acceptor HOMO of the second chromophore, and it forms the D plus a minus state, but it's intermolecular one. And by this definition, we can still have a hole hopping between two chromophores, right? And then just here, I want to stress the D plus a minus is energy favorable because the energy is a bit lower and than the exciton state, but the other state is just a little bit higher, so then not favorable. And so here, I just benchmark the aggregates in both J and H aggregation. So here, we have the energy setup still the same, the HOMOs line up, and the LUMO just had a bit downshift, and then just we let the intermolecular charge transfer coupling in phase, and then the couplings in phase, and that means they are both 0.4 eV. And then as you can see in the monomer is they have a little bit, and then just about the in the aggregates in red is huge band shift, and also the A1 gains intensity over A2, and if we check the energy diagram, so the monomer exciton energy level, as I just labeled their numbers around 1.77 eV. And but the diabatic CT state, intermolecular CT state, stay at the top of the band, around 2.5 eV. So, and they have really huge band gap right here. And then when we let them just coherent, we know the exciton stay at the bottom band, and they will be pushed down, right? And then just sorry. So and when we let them just cohere through the CT cell, the energy the energy the agent the A axis should split by the with the same way, and their energy difference should be the 2 times the stress of their effective coupling. And we use the second order perturbation theory to estimate that. And the interesting point is like there is a negative sign. Sorry, there's a negative sign in front of them. So they that means like in this case, when the TETAs they're all like +1, and then we got a negative number since the denominators are all like the like positive energy detuning or energy difference, right? So and then just so if the effective coupling is a negative number, so that means like it's a J aggregates, right? So and then we can imagine the brass state will go to the even lower energy levels as it go to the bottom of the band. So there should be a really huge redshift, and we can promise the without any mathematical derivation, the brass state will never stay above the monomer axon energy level because it goes to even deeper, right? So that's the normal Kasha J aggregation. But when we flip over the TETH, flip the face of the TETH, so that means TE is like 0.4 eV, and TH is minus 0.4 eV, and we keep the other settings the same, and then we definitely have a redshift H aggregates, right? So. And we can check the energy level diagram again. So when we let them just couple it again, and then just they will still have the same energy diagram, but this time the Coulomb coupling becomes positive. That means the brass state will go to the at the top of the axon band, right? So this one is the brass state right now. But the question is like there's no promise that the brass state will never go over the monomer axon state. No worry. So after like some derivation, so we have like a huge sorry, that's a really tedious one, but like if you we have an equation for the like the amount of the redshift. So with that, you can see the numerators are all like square terms. So that means they're always greater or equal than 0, right? But in the denominator is just a positive energy detuning. So the whole equation should be always greater or equal than 0, right? So that means that like no matter J or H aggregate, the axon state will never go over the monomer energy state. So that means it's always redshift, no matter J or H. And so here's the like the basic picture of the intermolecular CT couplings. So let's get back to check the Kasha theory, right? So they have the like redshift J, and the A1A2 ratio is enhanced, right? And then in the H aggregates, but the whole band is blue shift, but like the A1A2 ratio is smaller than the monomer case. But if we check our benchmark as theory again, so the lab one really follows the Kasha's rule, right? And redshift A1 enhanced, but the case on the right hand side totally contradicts the Kasha rule. So we still have a redshift, but like the A1H ratio is just A1H ratio just decrease. So that tells us like we in experiments we can not like the only like band shift cannot be like a reliable threshold to check the H or J aggregates. And we prefer to use the like A1 A2 ratio in the absorption spectrum, or like the if they are like emissive or non-emissive to check the H-J aggregation. So and later just with some like the parameters from the monomer spectra, and then just we run some TDFT calculation to get the intermolecular charge transfer coupling, and we reproduce their like the some like the experiment results, and as you can see we almost like they reproduce the redshift H aggregates and the A1 in the DPP chromophores case, and then just we have like A1 or A2 less than the monomer case, and we also reproduce the CT band at a higher energy level. But the drawback is still like clear, like we overestimate the higher energy band, and also with like in phase TNTH, and then we can reproduce the J case, still like the typical Kasha signature, right? And then just like we just also we move to the photoluminescence of the two PDI two DPPs, and then just as you can see, like we reproduce the like the emission spectra, and then just in the aggregates, both like both of the derivative have a huge redshift, and then just in the methyl derivative, as the emission is pretty weak, and it's just it's similarly activated photoluminescence. But in the cell iso derivatives, it's like super radiant, right? As you can see, and but also like here, like our theory just underestimate the like the 0-1 transition. So you can see in the experiments, like it's still like it's a little bit less than our slope. So that means there are still like some like missing terms in our Hamiltonian. So next, so since we have already built up like the CT-mediated scheme, like we turn to consider like more complicated case, like it's called like singlet-fission. So that means like the one singlet axon becomes two triplet states, and here like we will just confine us like with the intermolecular singlet-fission. So let's go for the big picture at the beginning. So if we shine a light, form axon in the first chromophore, and then we under some like mechanism like there's we can in experiment you can see the separation of the triplet the triplet pair state in the two chromophores, and this process is called singlet-fission. And then just later the two triplets axon will just disperse or like dissociate and become two independent states, and then just that means like the axon yield is doubled, and then just sometimes the efficiency of the photovoltaics is double, right? And later it can just get back to the ground state. But the mechanism of the singlet-fission is still confused, right? Someone believe there should be like direct coherent, but the others think that there should be some intermediate state, like let's say the charge transfer state. So since like in the experiments, like lots of guys like just to tune the efficiency of singlet-fission through the polarity of the solvents. So we believe that only the charge state could be stable or like tuned by the polar solvents. So so then the charge transfer mediate scheme should be a promising pathway. So then just we just focus on the like the EP-PDI in our research, and then just because our like collaborators, Dr. Chang Roberts, just like synthesize a series of that, and we will try to just like understand the mechanism behind the singlet-fission. So and then you can see like in their experiments, like they just have two different phases of the promote force, and one of the alpha phase is really chaotic, but the beta phase is well just crystallized, and then they have the different behavior. So we believe they're like vibronic peaks here, like the A1, A2 in the alpha phase are almost lined up, but they in the beta phase, like it's just like a little bit larger, and both the photoluminescence has a like huge redshift. We want to understand why, right? So so here like we just like still follow the previous slides for dimer system, Coulomb-coupling, charge transfer coupling between the promote force, and then but here like we include like the like triplet pair state, and which is a little bit lower than the the singlet exciton state. And since like the triplet state has no exchange contribution, right? So the energy should be a little bit lower. And then since we only focus on the CT media scheme, so we only let them just couple through the charge transfer states. And so for the like in the beginning, we have like some like really simple benchmark calculation. There's no vibrations, only like electron states. So as you can see, like when the in the beginning, like when the TTH of in phase and G1, G2, that's the coupling between the CT state and the triplet pair state, and then they're all in phase. And we can definitely show like see like three band, right? And then we believe that the lowest one should be the triplet pair state, because since it's at the bottom of the band, and the middle one is the Frenkel state, and the upper state is the CT state. But like as long as we flip over the sign between the Frenkel and the CT, and then there's only one bright band. And then if you check the band shift, like the Frenkel exciton here is almost stay at the like the original place, but this one is a little bit like blue shift. And then just like if we keep playing with the phase problem, right now in these two cases, like the G1, G2 is always out of phase, but we play with the T and TH, the phase of T, TH, and you can see like the different like picture, right? Like there are two bands, and but this one only like single bright band. So we want to understand. This is the quick summary of them, right? So only when they're all in phase, we see three bright bands, and then just like there are only like two or one. And only in this case we can see the bright pair states. So we have to understand the mechanism. So I think the key is the symmetry of the wave function, and that really like change their couple through the different state, and then we can have see. So to check the symmetry, like we have to use the K-adapt basis set, or like translational symmetry adapt basis set. So since the exciton state are neutral states, so yeah, dimer system, they could either have like symmetric state and anti-symmetric state. So the symmetry is like really similar to the like s orbitals, s atomic orbitals. So I just use like the square to express them, right? And then the CT states are like a charged polarized state, right? So the in phase or out of phase state, we should follow the p atomic orbitals, right? So because the charge polarized. And then just for the triplet pair state, so we can still have the symmetric and anti-symmetric state. And then just we can just use that the symmetry constraint to understand the magnet behind this singlet-fission. So here like, I only choose like two simplest examples for us. So first, there's the TTH and the GYG, they're all in phase. So under this one, so the symmetric Frenkel axon state should like couple to the symmetric CT state, and then later it couples to the like symmetric triplet pair states. And since only the Frenkel state will carry the transition dipole moment, so after like they are coupled, they will always like they all carry the transition dipole moment. And for the other three antisymmetric states, they stay just decoupled since they're coupling are out of phase. So that's the reason why we can see like three bright peaks in the absorption spectrum. But when we flip over the sign, like this case, like when they are all out of phase, that's the last case. And then so only the antisymmetric state will coupled, and then the symmetric state will decoupled. We will never couple. Sorry, this maybe something wrong there here, and we'll never couple together. So then, since only the symmetric Frenkel state carry the transition dipole moment, so we will only see the one bright peak, and then since it will not couple to the any other state, so they stay at the original place of the monomer energy. So that's the parity symmetry of the wave function. And here's my most recent result. So I just check the energy level movement between the symmetric and anti-symmetric. So when they are like in phase, like the symmetric state will coupled. So then the upper and the lower one are all symmetric states, and then the anti-symmetric state will not move. But like when they are out of phase, when the GYG coupling are out of phase, and then only the anti-symmetric states will couple, and then one goes up, the other goes down, but the symmetric state leave at the original place and it doesn't move. So since when the charge transfer state and the triplet pair state just will just push the energy of the CT state a little bit above, so we can assume the Frenkel-CT coupling is weakened, because in the beginning there is no this term, so they can be estimated by the TTH divided by the energy difference between the Frenkel-CT. But right now, like when we include the triplet pair state, the eta by the CT state is pushed up by this amount. So that means like the effective coupling is totally weakened. And then later, like we check it with the numerical simulation. And so in the beginning, like we run a calculation without the triplet pair state, and that's the red curve. So it's a J type, and the A1 A2 ratio is a little bit like this. So when we include the triplet pair state, and in the black curve, and you can see like the whole band has a little bit redshift, and then just the TT state becomes bright. That's anticipated by our previous the electronic calculation, right? And then if you check the ratio of A1 or A2, that's much less. That means the J feature is vacant. That's totally follows our the theory we just proposed. And okay, I think I can skip these two stuff, and then just back to the experimental results, and for the alpha and beta phase crystals. So we just use random TDF calculation to get some parameters for the beta and the alpha phase. And then just we run some simulation on that, and then you can see like we almost reproduce their like the axonic band, right? The AY2 ratio in the beta phase is like a little bit larger, but in the alpha phase it almost line up. And we also have the CT band at the at higher energy region, but the drawback is still like clear, like the CT in this case the CT state just is over at the intensity is overestimated, and also the band shift is not enough. So and then in the upper phase, like we just reproduce only one of them. So there may be some other exciton states at the higher level, and interestingly, like in both cases, the singlet-fission is really big because in the numerical calculation we found the coupling is always out of phase. So that means like they're like electronic forbidden. So we can hardly see them in both cases. So as a simple quick summary, like we just use our theory to reproduce the non-Kasha behavior in the chromophore and in the DPP, and also the we try to reproduce the triplet the singlet-fission and PDIs, and then the Frenkel Holstein model is really like powerful, like to understand the axonic behavior in organic solids. And finally, like thank for my PI to really like give me the chance to present my results, and thank for the support from my lab mates, and thanks for the funding support. Thank you for your attention. Thank you so much.
We have time for a couple questions. I'll get started with a question.
Okay.
So for your model with the donor acceptor donor pores, you assume that each donor and acceptor are the same, or are they slightly different?
You mean the energy level or the
Yes, the energy level.
Yeah, so as you can see so I only show like one case, like we call it sorry, that's what we call the type 2 chromophores. The homos line up, and the lumos like has a little bit different. And if you check my previous paper, like we consider like 3 cases, like the type 1 and like the homo lumo have almost the same energy downshift, and then in the type 3 the acceptor forms like a sandwich type. The homos like 1 EV higher than this one, and the lumo is like 1 EV lower. So they stay in the middle. So like yeah, but because the reason I only show this case because the redshift is pretty strong in each case, but in the other 2 cases, it's a little bit weak, but they are still like redshift. Yeah. So yeah. Any questions?
Question
Yeah.
on your graph. It's a organic nanoparticle.
Yeah. So
I just want to know what is the size.
The size of the nanoparticle is around like 30-40 angstrom, like a little bit. I totally forgot the detail. So you can, I'm sorry, like you can check the Pontis paper, like they provide the details in the ESI.
Carlos?
Thank you for the presentation. When it was presented and calculated results, the experiment, you mentioned that the mismatch maybe was because of some missing terms with
Yeah.
system. So have you thought about what terms are that?
Yeah. So the frequent answer is disorder. So like because like in our model we only consider the on-site vibrations. So there should be like Herbert-Tyler coupling. So that means the vibration on this side just spread to the other side. And also you know in the organic solids it's pretty like soft. And then there's like the intermolecular like the packing is not so solid, not like the inorganic like TMPs. So they could be oscillate. There's even their piping in the crystal, they will still oscillate. So you can imagine like the charge state really sensitive to the distance. So when they are oscillating, so the TETH or like maybe like changed by their oscillation. So and if you check Dr. Spano's most recent paper, like they have the they call it Paris model. So we can still add them in the code, but that makes the code really like chaotic. And then later, like you can also consider that the packing disorder, like in lots of like effects. So yeah, and also we only have the linear absorption term. So maybe like in the practical there should be like nonlinear term. So this is only like the most rough approximation. So yeah, there should be lots of effects.
Yeah, that's a good thing. Great talk, thank you. You know, one of the things I just love is you just have such a systematic approach to doing this. Are you all thinking and working with Sean? Are there ways that you can also tweak the experiment to tune to the theory a little bit in terms of removing some of what you might see as from the experimental side as being kind of noise? If this is in case we can remove this and to fit the theory as opposed to the other way around, right? Just trying to adjust the molecular level.
Yeah, so yeah, I should say like the theory is like a little bit simpler than the practical experiment. So right now like the procedure, like the routines, like we build up like we start from the really simple theory, and if we cannot just reproduce the experiment, so we try to like consider like how to just like break the symmetry, like and then maybe like there's some symmetry breaking in the wave function, or like add some terms. So so that's the typical way.
Yeah, it's always, the theorist always has to adjust the experiment. Let's make them adjust back.
Go Nick. So when it comes to your simulations, how are you guys running those? Are you guys writing your own simulations from scratch, or is there some sort of like already published simulation that you might be adapting from?
Yeah. So so first like we can just start from the monomer case. Generally speaking, we start from monomer case. So lots of like parameters, just like so I think I have some I delete that slide. So we can check the 0,0 transition in the monomer. So they give us the like reference level of the axon, and then maybe check their like the vibrational spacing between the vibronic peaks, and they give us the effective vibrational quantum, and also the like the A1 A2 peak tells us the like one risk factor, right? And then later, like for the aggregate case, like we have to calculate their like TETH coupling that cannot be shown in the experiment. So we run some like TDDF calculation in the Gaussian package. So I prefer the Gaussian package, and then you can still use the other like quantum chemistry method, and then just so for the like the energy of CT state, we mainly just check them from the monomer and the aggregate case, and also we can also run some like the TDDF calculation, but like in like DFT theory, like they only consider like single Slater determinant. So for the excitation state, there's not the agent state of the total angular momentum. So there must be some like mismatch on the is always like overestimate. So yeah, so sometimes we can only just like tune it up or down, like try to feed our result with the like the very result.
Thank you. Last question.
So I have like 3 short questions related to one thing that you mentioned earlier. So you mentioned that singlet fusion leads to photovoltaic efficiency that's beyond the Shockley-Kessier limit. So my first question is, why does singlet fusion lead to more efficiency? 2 is, how much more efficient is it compared to the Shockley-Kessier limits? And 3 is, how practical is it to apply this ideas and materials used for photovoltaic devices like solar cells?
So for the like singlet fission, you can think about like this. So we shed light to the chromophore, right? We only have like one axon in the chromophore 1, and later like, under some mechanism like they form like the triple axon on the chromophore 1, and another triple axon with totally downspin on the chromophore 2, and later they will just separate. So that means like we have like 2 axons on both chromophores, but in the beginning, like we only form there's only one axon forming. So that means like the number of the axons totally double. So there's that means like the quantum yield is double. So if we can just tune up, like make it like really strong, like then there's like maybe in the future we can we can build up like really high efficient like solar cells, and then that depends on how we control the intermolecular coupling, right? And sorry, what's your next one?
Oh, you already answered the first one. It's like, how practical is it to have materials applied to photovoltaic devices like solar cells, like in the future?
So I should say like our theory can only answer like part of their like the mechanism to how the axon coupled, and I think that Dr. Sean Roberts also asked me the similar questions, like if we can just anticipate that. I should say that really depends on the accuracy of the like DFT calculation or the accuracy of our model. So you see our model is pretty simple, like. So I'm not so convinced like we can just really anticipate some like practical features in the experiment. So, but I should say it can just give us like maybe like 70-80% accuracy, right? So at least like we can just exclude, like help us like exclude some like unfavorable candidates, right?
Let's take your studio.
Hey, Greg. At the end. Yeah, pretty much what I mean. It was good. Later. Like I have like movie before, so if you're around, yeah. I figured you.
Great job.
Thank you so much. Let me we need to stop sharing.
Yeah, stop there. Perfect. And here, I'll do the rest here.
That was awesome. All right, that was great. Thank you. That was really enjoyed that. Yeah. So I'll leave you in Jaime's hands.